Hello everyone. Today we are going to talk about partial differential equations, or what we also call as PDEs. So I want to first define a general form of PDEs and then talk about the some classical equations of PDEs, or some canonical homogeneous PDEs, and define some of the famous PDEs that you need to know and their classification. Okay, so let's first get started by defining the second order PDE and how does it look like in a general form. So a second order PDE in two variables is an expression of the form f. So I'm going to write it in a general form. What is the second order PDE look like? F x y u ux uy uxx uxy uyy equals to 0. Okay, so first this is a second order ODE. Let me show it with this. This is a second order ODE and PDE, and it is in two variables. So I have two variables, x and y here. And so these are my two variables, which we call it independent variables. U here is a dependent variable, so u can be a general function of x and y, and it is a dependent variable. Okay, and let's I have another definition. What is ux uxy? So this is just a notation. So uxy, we just define it. This is a derivative of u with respect to x and y. So this is just a notation. And similarly for other terms like u yy, it's gonna be d2u partial u over partial y square. Okay, so this is just some notation, and this is a general form of a PDE that we define here. And f is generally nonlinear. So it's not necessarily linear, it can be a nonlinear function of these. So we can have like a combination of all of these together, like xy, or like ux times uy, something like this. So these are all, this can be a nonlinear function. Okay, so now I want to define a simpler version of this, general formula for PDEs, and that is a linear PDE. So let's see what happens if you have a linear PDE. So a second order linear PDE in two variables. So again, in two variables, has the form. So this is a second order, so and it's linear, and we have two variables. Okay, so the difference here is that now this is just a linear function combined to the previous one, which was a general form. Okay, so let's see how does it look like. So it has the form of this: b x and y, as it can be a function of x and y, plus a0 xy u plus a1 xy ux plus a2, which is, these are coefficients, a2xy, which means is can be a function of x and y, uy plus coefficient a11, which can be a function of x and y, and uxx, the second derivative of u with respect to x, plus a12 xy uxy plus a22 xy uyy equals to 0. Okay, so this is, if we have a linear PDE, then this is gonna be the form of a second order linear PDE. Okay, so now I want to make some definitions. So one definition is if b, x, and y is 0, this equation is called homogeneous equation. Okay, we call it homogeneous PDE. Then the other definition is a little bit more general, and some authors and some books consider this equation, this definition is that if b equals to a0 equals to a1 equals to a2 equals to 0, so all these first order terms and zero order terms are 0, then we call this as homogeneous second order PDE. Okay, so this equation is going to be homogeneous second order. If, on the other hand, if b is equal to a0 equals to a11 equals to a12 equals to a22 equals to 0, this is homogeneous first order equation. Okay, so these are some definition what we mean by homogeneous. So if all the for example, let's talk about the homogeneous second order. So homogeneous second order means that these terms, so let me show it here. So these terms all should be 0, and we are going to only have these terms. Okay, so this will be a homogeneous second order equation, which is coming from here. Okay, so these are just some definitions. And now I want to talk about an important part and topic, which is some classical equation of math and physics, or some canonical homogeneous PDEs in two variables. Okay, so these are some of the famous equation PDEs that you can see. Okay, so the next topic is gonna be classic equations of math and physics, or canonical homogeneous PDEs in two variables. Okay, so let's see what are these important equations. Okay, so the first one is first order advection equation. So when we talk about advection, you should always remember this equation, and this is first order advection equation. So the form of it has a form of du over dt plus v can be a constant, du over dx equals to 0, or another form of it, you can just write it in this notation, ut plus v ux is 0. Okay, so this is called advective transport equation. And we will come back to this, why this is an advective transport equation when we talk about method of characteristics, and we show how this equation looks like. The solution of this equation looks like. Okay, so this was the first equation, famous equation. And second equation, which is a second order equation, homogeneous PDE, is wave equation. So second order wave equation. Okay, so let's see what it is. So this we can write it in as d square u over dt square minus beta square d square u over dx square equals to 0, or we can write it in another form, which is utt equals to c square grad square u, or if it is a 1D, if it is only two variables, so if we only consider one direction in a space, we can just simplify it to utt equals to c square instead of grad u, which can be a general function of any dimension in the space that you have, or even higher dimensions. You can just write it as uxx, so just one dimension. Okay, so this one, if u has n dimension, we have one which is time plus n dimension of u independent variables. Okay, so one dimension of t, which is time, and n dimension of u is going to be 1 plus n independent variables. And this one, we only have one time plus one x, so it's two independent variables. And another side note is that the type of this equation is hyperbolic. So this is a hyperbolic equation, and I'm going to come back to this point, what does hyperbolic mean and how we can get to this later on, after we talk a little bit more. This is gonna come after the method of characteristics. Once we find the characteristics of these PDEs, we will come back to this point. So the third equation is the heat equation. The heat equation. So this is actually how the heat spreads. So the heat transfer is is solved with this equation. Also, it is transient flow equation, known as transient flow equation, has this. So let's see how it looks like. So this is one form of it in one dimension, dH over dt minus d square h over dx square equals to 0. So this is first order. This is second order. Or we can write it as ut is alpha square grad square u. Again, this is in a general form, and this has 1 plus n independent variable, because of 1 is time and n is from u. Or another way of writing this is let me write it here. Ut, if only u has one dimension, we can write in one dimension, we can write it in xx, alpha square uxx. And the type of this equation is parabolic. And I'm going to come back what does this mean. So this is the is known as heat equation. So this is how the heat actually spreads, and it's very important. And the last equation that we are going to introduce here, the last homogeneous second order equation, is a famous equation known as Laplace equation. Okay. So Laplace equation, also steady state flow equation. So all of these have time dependency in them, so they are all transient. So the third one is known as transient flow equation, but the last one doesn't have time, it's only in space. Okay, so this is what we know as a Laplace equation. So this comes a more general form of that. I will first write that. So is divergence of kappa or k grad h equals to 0, and if k is constant, then we get divergence of grad h or Laplacian of h equals to 0. Okay, so this is the Laplace equation. Or we can write it as grad square u equals to 0, and here we have n independent variables. Or another way, we can write it in two dimension, uxx plus uyy equals to 0. So in two variables. So here we have two independent variables. Okay, and this equation, the type of this equation is elliptic. And again, I'm going to come back what do these three types mean when I talk about the method of characteristics, okay? So these are four canonical homogeneous PDEs in two variables, and these are very important for you to know. First order advection equation. So this is a first order equation, also known as advective transport equation. Then we have second order wave equation. So it is a second order equation, and we mostly work with this one. So this is second order, and the type of it is hyperbolic. The third one is the heat equation, which shows how the heat actually spreads out in space. And this is the form of the equation, ut equals to alpha square grad square u. And then the last one is the Laplace equation. So we show it as grad square h equals to 0, or ux x plus uyy equals to 0 in 2 dimensions. This can be in 3 dimensions or in higher dimensions as well. And then the types of these, which we will talk about them later on.